All right. 2010, question 6. First thing is, oops, I probably should have made sure my pen was working. First question is, so basically, respond to the following statements and questions related to the species and the reaction represented above. This is probably going to come up later, but let's just do it right now. So, aluminum is oxidizing. Why? Because aluminum has a zero charge, because that's a pure element on the left, and it has a +3 charge on the right. Um, and then zinc is reducing because it has a +2 charge on the left, but it has a zero charge on the right. And so remember, if there's nothing there, it's an assumed zero. But anyhow, the first question is, what's the complete electron configuration for zinc? Now note zinc, a zinc ion. And so what I would start by is I would get the zinc electron configuration. Zinc is, oh, and it says the complete electron configuration. So 1s2, that's the first row, and then 2s2, and then you jump over that hole, and then it's 2p6, and then it's 3s2, and then it's jump over the hole, it's 3p6. And then you're in the fourth row and it's 4s2. And then when you cross that line, now it's the d orbital, because remember, when you're in the fourth row, the d orbital that's filling is one less. And then that's it, because 2, 4, 10, 20, sorry, 2, 4, 10, 12, 18, 20, 30, and zinc is atomic number 30. Now, the interesting part is it didn't ask for zinc, it asked for zinc +2. And remember, they don't come out the way they go in. The valence shell comes out first. Now that you understand bonding better, we can go back and readdress this. When a zinc atom approaches a nonmetal to bond, what bumps is the valence shell. So interesting. The electrons go in low to high energy. They come out outer shell to inner shell. And so zinc, I don't know if you'd have to rewrite it, but this is zinc after you, the zinc ion. And now this is really important because of the next question. Um, if you'll notice, a zinc atom has its valence electrons are in the fourth shell, whereas a zinc ion, when you get rid of this for they're in the third shell. Um, and if it's in the fourth shell, then the shielding electrons are the first, second, third. So there's 2, 4, 10, 12, 18, 28 shielding electrons. But if you're in the third shell, then the shielding electrons are the first and second shell. So before I go to the next problem, you can see from this that a zinc atom has the valence, the zinc atom has its valence electrons are in the fourth shell, and it has 28 shielding electrons. But a zinc ion has its valence electrons are in the third shell, because those are gone, and the shielding electrons are the inner shell electrons, which are the first and second, and so it has 10 shielding electrons. So before I go to the next thing, here is the next question. Which species had a greater ionization energy? Justify your answer. So now here is my template. Remember, when you have these equations, you need to talk, we're going to talk about shells and shielding electrons. We are not going to talk about effective nuclear charge, because they both have an effective nuclear charge of 30. Okay. And if this was about size, we could talk about, this one has less this one has less electron repulsion, but this is not about size, it's about ionization energy. So we're going to talk about shells and shielding electrons and how that affects Coulombic attraction. Because remember, all of this stuff from chapter 8 goes back to Coulomb's law, because the atom is a little tiny it's a little tiny magnet, where the positive charge is in the nucleus and the negative charge is in the cloud. And then how no when strong at coulombic attraction and how that affects how tightly, this is Mrs. Hyde's terminology, but you just got to convince the graders you know what you're talking about. The valence electrons are held. And then after that, how this affects ionization energy. So in other words, if the valence electrons are held really, really tight, it takes more energy than if they're not held as tightly. So here is kind of our, so we're going to talk in the first, so remember all chemistry essays can be answered in 1, 2, or 3 sentences. So when I go to do this, I'm actually going to add a new slide right here, blank. We would say, now, please don't look at the scoring guidelines online. Even though this problem is from 2010, they changed in 2013 how we're supposed to teach this. So the scoring guidelines for 2010 are different than the scoring guidelines for 2013. From 2013 on, you have to talk about shells and shielding electrons or ZEF, how that affects coulombic attraction, how that affects the pull on the valence electrons, and how that affects either size or ionization energy. And you need to talk about both species. So what I would start, always answer the question, what has the greater ionization energy? Zinc plus 2 has the greater ionization energy. First sentence, answer the question. Now, so then and you don't have to say it in both parts of the compound sentence, but you need to say, here's my justification. Zn plus 2 has less shells. Remember we said that has 3 and less shielding electrons. I guess I shouldn't say that. Let's say fewer. It has fewer shells and fewer shielding electrons than zinc. We can just use it. Some linking word. Thus, or so, or hence, thus, Zn plus 2 has stronger coulombic. This coulombic is huge. It means I taught you about Coulomb's law. Zn plus 2 has stronger coulombic attraction for its valence electrons. That's sentence 2. Sentence 2, you're supposed to talk about shells and shielding electrons or ZEF and how it affects the coulombic attraction. Zn plus 2 valence electrons are held more tightly than Zn's than zinc's valence electrons. So, okay, I'm gonna, let's see, I think I can push this, hang on. So it takes more energy, because we're trying to explain why it has a higher ionization energy. It takes more energy to remove a valence electron. And I want you to see how many times I said valence electrons. Let me get the different color because it's hugely important. Okay, greater, okay. So thus the N plus 2 has stronger coulombic attraction for its valence electrons. Zn plus 2 valence electrons are held more tightly. By the way, you could say zinc ions and zinc atoms, then zinc's valence electrons, and then again valence electrons, and then coming down here, probably should have another linking in here. So it takes more energy to remove a valence electron. Okay, over and over and over again, talk about valence electrons. All right, number 3, enough said. What species is oxidized? We said aluminum because it went from 0 to +3. Move on. They didn't say explain. 5, a diagram below shows a galvanic cell based on the reaction. Okay, the diagram includes a salt bridge that is filled with the saturated KNO3. Describe what happens in the salt bridge as the cell operates. I cannot tell you how important this is, and it's not that hard of a concept because you just got to think about the definition. So let me just get this. So here's the deal. Everything starts with oxidation because oxidation is lost. The aluminum has to lose the electrons before zinc can get them. Now, in our example, you can see that aluminum is oxidized because it's going from 0 to +3. So anyways, the electrons leave the aluminum. And so here's what happens. The aluminum, if you look at the half cell, the aluminum atom turns into an aluminum ion. Okay, so here's what happens. If you want to balance it, this side is 0, this side is +6. So this has to be -6. So 6 electrons per atom leave. Okay, now here's the deal. So the aluminum metal turns into an aluminum ion. A couple things happen in this half cell. The aluminum mass goes down. Why? Because the aluminum metal is dissolving, turning into an aluminum ion. The aluminum mass goes down, but the concentration of the aluminum ion goes up. Remember, because if conservation of anything, the aluminum metal turns into aluminum ion. So this gets smaller and this gets larger. Now, this conversely, in this cell, this, by the way, this is the oxidation half cell. This is the reduction half cell. Now, as the electrons travel through the circuit and they hit the zinc, what happens is the 6 electrons on the interface between the metal and the solution, they come down here. And what happens is that the electrons, because this is what you have 3Zn plus 2. This is what's going on in the reduction half cell. Plus 6 electrons, goes to 3Zn. What happens is these electrons come over and they come down the metal, and the electrons hit the zinc in solution. And what happens is, you can look at this equation, you're making zinc metal. In the reduction half cell, the zinc metal mass goes up because you're making zinc, whereas this goes down. But then this is interesting, the zinc concentration goes down because the equation tells you that the zinc ions in solution are turning over to zinc metal. Now, what you need to know about, because now they're asking about the salt bridge. So what happens is, because in this cell, the Al+3 concentration is going up, the battery will quit working if you have too much positive charge. They need to be balanced. And so what happens in the salt bridge is that the nitrate ions migrate into this cell because the extra positive ions react with these negative ions, and it keeps the charges balanced. So what happens is the NO3 minus 1 ions in the salt bridge move into you could either say the oxidation half cell or the aluminum +3 half cell. Now, consequently, look over here, the zinc +2 concentration is going down, which means you're going to have too much negative charge. And so to counteract that, the K moves into that, because if this is going down, you have too much you have too much negative charge because you're losing positive charge, and so you have to balance the extra negative charge by having the positive ions. Over here, the positive charge is getting bigger, and so you have to get rid of the positive charge by having the negative go in. So then the other thing that happens, and I'm not entirely sure, you can look at the scoring guidelines on this. They haven't changed the scoring guidelines on this, but what you need to say here is that the that the K plus ions in the salt bridge move into the zinc metal zinc ion half cell. By the way, this is the oxidation half cell, and then this is the reduction half cell. All right, next slide. What is the value of E for the cell? So what you have to do is you have to go to your sheet, which I don't have put up, but this is, so this, we don't do the states, but let me just tell you. So this is oxidation. Now, back in 2010, the reduction potential was one of the sheets, and these are reduction potentials. And so what you have to know is this is not a reduction, this is oxidation, so you have to flip it. And then you have the zinc goes to zinc. This is a reduction because notice the charge is going down. So if you go to the sheet that you have, I didn't pull it up, but if you go to the sheet that you have, you will find out that this on the sheet, anyways, what do I have? I have 1.66 volts plus negative 0.76 volts, and then this is 0.90 volts, and that is a positive voltage. So this cell does generate current. And then give me a minute, I have this thing right here. So on the sheet, it used to be the third page of the old test, and this is from the old test. But when I find zinc on this sheet is Zn plus 2 electrons goes to Zn, and it says right next to that that's negative 0.76. So this is negative 0.76, which is right there. And then aluminum, now remember, this is reduction potentials. But if you look up here, aluminum is reduced because it's going from 0 to plus 3. So this one on the sheet is, it's, I don't know, where are you? It's, I don't know, about 1/3 from the bottom. This reduction potential is negative 1.66 volts, but because this is reduction and this is oxidized, I have to flip it and it becomes positive. And so, and keep in mind, you do not use these numbers. This is an intensive property. It does not depend on the mass. And basically, if I go back, I'm going to say this a whole bunch of times. All of this stuff occurs on the interface between the solution and the metal, and so the mass of the metal does not matter because it doesn't use the whole metal, it just uses the surface. And so we don't ever multiply by 2s or 3s. All right, indicate whether the value of G is positive, negative, or 0, and here's the thing. If you have a positive voltage, that means it is generating voltage that is a spontaneous reaction, because that's what you need a battery to do. You need it to spontaneously generate voltage to run the calculator or the computer. Now, in electrochemistry, if the voltage is positive, it's spontaneous. In thermal, if delta G is negative, it's spontaneous. So, and so I don't know, remember this, there's a relationship between G and E, but basically there's a negative sign in the formula. And basically, what is it? It is delta G is equal to negative 0.0257 over N. Oh no, that's LNK. That's the wrong one. Never mind, just do that. It's spontaneous. All right, I'll come back. If the okay, now this is the hardest problem because this is the Nernst equation. And so here's the deal. This is what you need to think. All right, so here's the Nernst equation. The cell voltage at non-standard conditions is equal to the cell voltage at standard conditions minus 0.0257 over N times the ln of Q. This is the Nernst equation. It's not on the test anymore. So here, you just got to say if it increases, decreases, or remains the same. All right, so here's the deal. Here's the reaction. Let me say it again. So 2Al and that's a solid. This is why they give you physical states, by the way. Hold on, I got to grab this eraser. Okay, let me just try again. All right, pen. So 2Al solid plus 3Zn plus 2 aqueous goes to 2Al plus 3 aqueous plus 3Zn solid. Here's what Q is. Q is what you call K when you're not at equilibrium. It's calculated the same way. Now remember, what's not in equilibrium constant? Pure solids and pure liquids. And so Q is the concentration of aluminum ions squared over the concentration of the zinc ions cubed. And now the question is, and notice, here's why 1 doesn't matter, because let's say this is 1 molar. 1 squared is 1. 1 squared is 1 cubed is 1. The ln of 1 is 0. And if all of the concentrations are 1 molar, this whole term drops out. But now this is what this question is saying. This is still 1 molar. But this now, here's what they want you to do, mathematical. This now is 0.010 molar. And so you can see that 0.010 squared divided by 1, Q is less than 1. I don't even care what it is. You can calculate it if you want. The natural log of a number less than 1 is negative. So this is going to always, so this is, I'm going to think of this, as subtract. So 0.0257 is negative. N is the number of electrons transferred, which is 6. And then the natural log of a negative number is negative. So this is positive. This is positive. But this term right here is negative because it's less than 1. And a negative, so E naught minus a negative number would be E naught plus, because a negative, some positive number, which means the voltage is actually, the new voltage is equal to the old voltage plus some positive number. So it increases. And then you have to explain all that with words. Q, this would be the expression for Q. You can obviously either do the math or see from here that Q would be less than 1. And so 0.0257 divided by 6 times the natural log of a number less than 1, this whole term here is going to be negative. And a negative minus a negative is positive, which means the cell voltage goes up. All right, I hope that helps.